Production support for Hot and Cold is brought to you by American Solar Technics, manufacturers of components for wood burning and solar heating systems.
Hey, I'm Tom Gosey. Welcome to Hot and Cold. Well, it wouldn't be a complete season without making a trip up to Orono to visit with Dick Hill, and Dick has prepared for us a comprehensive study of frost heave in the state of Maine, which is going to be a very interesting subject because it relates to how we build our houses, how we build our foundations and sidewalks and driveways. So we have some great stuff to look at today and great graphics, and we've got Dick Hill to boot. It's going to be a fun show. Stay with us. We'll be right back. Well, we're back. Dick, thank you for taking the time to chat with us. This whole idea of frost penetration and what it does to buildings is really sort of a northern climate problem.
That's right.
And people in North Carolina, Florida, they just throw something on the ground and it never moves. They put the sonotubes in the ground and the hurricanes don't blow them away, but up here we have some issues.
That's right. But there have got to be three simultaneous events in order to get frost to act against a building. First of all, there's got to be a frost-susceptible soil. There's got to be a soil that will pull moisture from the subgrade by capillarity up into the freezing zone.
Okay.
Now, if you don't have that kind of a soil, you don't need to do anything.
So if you're on a gravel or a sandy soil,
right,
you'll not see a frost problem.
That's right.
Now, when you say frost-susceptible soil, we're talking about clay-type things, silty things?
No, if it's really thick clay, the moisture won't move through it.
Okay.
So you can get by with that. It's the silty soil.
So it's the clay that you can't dig through is okay.
That's right.
That's easy.
Yeah. So a lot of people get away with garages and porches and stuff in Maine without any problem at all because they have failed to meet one of the three criteria. Either it isn't frozen, or B, it isn't frost susceptible. And that we have a picture here of how these three events work together.
See, we do this on the radio, but now we have the picture, which is worth 1,000 words.
The thing that is non-common sense about this is that most people think that frost movement is associated with the fact that when water becomes ice, it expands. And that's what makes frost heave. That's not right.
Okay.
What happens is that this is a sidewalk here, and it gets cold outdoors, and the moisture in this layer begins to freeze. I've drawn a line here, which is presumably the 32-degree Fahrenheit line.
Okay.
Now the trick here is that once this water turns to ice, the ground acts as though it is dry.
Okay.
And it sucks moisture from the subgrade. And what happens is, instead of simply getting frost in here, you get an ice lens that grows and grows and grows. And that's what lifts the sidewalk.
I see.
It's this sucking of moisture from the subgrade. Now, if you could put some kind of a barrier in here so moisture didn't come up from the subgrade, then sure, the ground would freeze, but it wouldn't heave.
Okay.
That's because the change of water to ice really isn't a very big volume change, and that wouldn't make a very big difference. One of the interesting aspects of this is, let's assume there's a rock in here. Now the rock is a pretty good conductor of heat and has no moisture in it. So these ice lenses will form under the rock before the ice lenses will form in the surrounding soil. And you've seen this over and over again, where a rock will come right up through the sidewalk. And that's because these ice lenses form underneath. The reason for that is that as the 32-degree temperature moves down through the soil, it moves very slowly because it must pump the heat out of the water to get it to change to ice.
Right.
So the 32-degree line appears very quickly underneath the rock, and that forms the ice lens, and that begins to lift the rock up through the sidewalk. So the next problem that all Maine people face is what do you do about a post? And concrete posts, as you and I know, are lethal. They're lethal for several reasons. First of all, the concrete is a good conductor of heat. So the 32 degree line, the freeze line, moves very slowly through the soil as the weather gets cold and radiation comes up here. But that 32 degree isotherm dips very strongly around the post because the heat can flow out of the post into the
post is
the
very
atmosphere.
conductive.
Post is very conductive. And of course the other thing is that this soil has got moisture in it, so it freezes very slowly. But the post doesn't have any moisture in it, so it freezes very quickly. And that of course sucks water out of the soil, forms this ice lens, and the ice lens grabs the post, and now that will tend to lift the post out of the ground.
So this is probably the absolute worst material we can use for posts. I mean, there's situations you have to use it, but you have to protect it from this kind. You have to understand the physics, I guess.
That's right.
So, and I've been thinking about that. The one thing that we do is try to get people to understand the physics behind why the post pops out, why the foundation moves, because this is pretty arcane stuff. I mean, it's simple. I mean, when I sit here and listen to Dick Hill tell me this, go, oh yeah. But the reality is, if you're just doing this on your own, it's it takes years of trying to figure out what the heck's going on, and here we are with a man with 50 years of experience doing this stuff.
You've said several times, Tom, and very correctly, that this is a pressure-treated wooden post.
Right.
Several things happen. First of all, if you wrap it in plastic, several things happen. First of all, the wood is not a terribly good conductor of heat.
Right.
So you don't get this what they call ice lenses freezing on the side of the post, which means subsequent freezing then lifts the post. That doesn't tend to happen. And you've always suggested that even if you use a pressure-treated post, you wrap it in plastic. That means this ad freeze, as they talk about, can't grab the post. It grabs the plastic and maybe moves the plastic on the down, but the post itself doesn't go. So putting posts in the ground, one has to pay attention. And here's a way of putting posts in the ground. If all you've got is a vertical load, like a porch, you can dig down, and as you and I have said many times, the limit of the digging.
It's autumn in Maine, isn't it?
Yeah, that's right.
There we go.
The limit of digging is until the digging gets tough.
Right.
You get down through the easy topsoil. Now you can put in an insulating pad, put a concrete block, and they make some very special concrete blocks that are made to accept a wooden post. And then you fill it with just any loose backfill, non-frost susceptible material. Now the 32 degree freeze line will go down very fast in the surrounding soil because there's no barrier, but that freeze line will stop at the bottom of the foam, as you can't pull enough heat out of the ground to get it to freeze in this zone here. So the post then will not heave if you put this layer underneath the...
And what we need to point out is this piece of insulation is usually 2-inch styrofoam.
Right.
This is a pressure-treated wood post. It's not just a piece of hemlock that you got at the mill. It should be pressure-treated. Yep. And these blocks, you can make your own, or you could go to a lumber yard where they do sell, as Dick says, something that's made to accept the pressure-treated, usually a 4x4, right into it. So this becomes very simple. Any character like me with a shovel can just kind of scratch away some soil. And the idea here is that we're protecting the foam from sunlight. We're protecting it from wind so it doesn't break up if it's windy and blow away.
Because one disadvantage of this, it gives the structure no stability this way. So that you've got, when you frame the structure now,
you need to brace it.
You need to brace it.
Sure.
Whereas the concrete post sunk deep in the ground gives you a little lateral stability.
Sure.
Now, we come to the problem of a slab on grade. And a lot of people are doing this now because the water table is so high in Maine, people don't want to put in a foundation in a cellar and all the rest of it. And a lot of research has been done on this. Papers have been published that take every frost domain, every weather domain, and design what must be done. And the trick here, of course, is we take an arbitrary point Q here, which is below the footing. That point can't drop below 32 degrees. Now that's fighting a battle between wanting to give up heat to the outdoors and wanting to accept heat from the building. And the makes a tremendous difference if the building is heated. This says heated building cross section. And there's a paper that we've published that has all this data in it that talks about what the dimension D has to be and what the thickness of the insulation is and so on. And it turns out, Tom, that the amount of insulation you need here and here to prevent frost penetration here is trivial. It's something like 3/4 of an inch of foam, and nobody would do that because you got another problem. You don't want walk on a cold floor.
That's right.
So you and I and anyone in the business would recommend 2 inches of foam here and here,
Right.
which is more than what you need.
Right.
If all you're interested in is protecting the foundation against frost heave. Now, one thing we didn't talk about here is someone looks at this drawing and says, how much concrete do I have to put in here? We don't talk about that. That's a structural problem.
That's we'll get an engineer to figure that out.
That's right.
Structural engineer. We're
Yeah.
talking about thermodynamics today.
But if it's a small slab,
Yeah.
obviously it'll be stiff enough on its own. You won't need any of this business at all.
Right.
Now, this is a warehouse, and it's
Yeah.
150 feet long,
Yeah.
and you don't want the frost to move a corner of it.
Yeah.
Now, you not only do this, but you've got a freight car load of steel bars in
Sure,
it if
sure.
it's a big, long structure. So I want to emphasize that what we're talking about here has nothing to do with the load that you're going to put on the building and the structure of the building. All we're talking about here is to prevent the frost from penetrating underneath the footing and ice lenses forming that is going to tip this up
Okay.
and
Now,
break the slab.
we should point out also that many garages, probably for the past 50, 60 years in Maine, this isn't here. This
That's
is
right.
just over because this structure is very small and light.
Right. Now remember this, there are 3 things now that destroy a structure from frost action. One is temperature, one is moisture, and one is a frost-susceptible soil. Now, an awful lot of satisfactory buildings that are built in Maine, they don't have any foam in them at all.
Right.
But they got them up high enough.
Yeah.
They got them well enough drained.
Yeah.
So they don't have a frost-susceptible soil underneath them. Now, a lot of people are going to look at this and say, this is a lot of baloney. That is, you don't really need to do this. I got a garage out there. It's never moved. Well, they're lucky. It's on a soil that is not frost susceptible.
Yeah.
So this is sort of a protection against the possibility that the ground, as we showed in the first picture, may suck water from the subgrade. That forms ice lenses, and pretty soon the building is being jacked up in the air.
And we have a couple more pictures. Then we're going to look at some real life.
Okay.
There's enough around. Anywhere you go, there you can see these frost problems. But
Yeah,
let's
well,
look at this.
the slide before, Tom, showed a cross section through here. It showed
Right.
the foundation and the wall and so
Yes.
on. This is a plan view. This is
top
looking
view.
down on the top.
Yeah.
And in our paper, we talk about what this dimension ought to be, and obviously you ought to beef it up on the corners because the corners are more vulnerable than the running slab is.
Yep.
So that the dimensions here are all spelled out in a little paper that we
We're going
publish
to
along
a
with
handout.
it.
We're going
A
to
handout
offer
we're going to have
folks.
available. There's
Yeah.
no point in shouting out the numbers because people will have to.
They're going
sit
to
up.
change the cartoon show.
Right. Now, this is kind of surprising. The same journals that publish the kind of information that we've described on the previous drawings also publish information if you don't have a building on top.
Yeah.
This now is, I think of this as a shuffleboard court.
Sure.
You're going to put it right outdoors and keep the snow off of it.
Yeah.
Boy, now you've got a problem because you don't have the heat transfer from the dwelling that goes
Right,
down into
right.
the subgrade. And the people that design these things, and taking this drawing from one of their designs, Tom, this distance is 7 feet.
Wow.
This thickness is 5 inches.
Wow.
This is what you need if
Yeah.
you're going to let the slab look at the sky.
Yeah.
All right. People don't do that.
Sure.
Why don't they do that? Put enough gravel in, jack it high enough up in the air, get it well enough drained, so you don't need to do this.
Yeah.
But if you're in a frost-susceptible soil and you
Yeah.
don't want that slab to move,
If you don't want it up high.
if you don't want it up high, then this is what you've got to do to protect it. Now, see, in the other picture, we didn't have any protection under the slab at all
Yeah.
because we assumed it's a heated building.
Yeah.
Now, with an unheated building, this might be a warehouse or a shed where this is going to be open to the night sky
Sure.
and so on. Now you've got to put insulation under the whole thing.
Yeah.
Otherwise, you'll get ice lenses forming in here and you'll get the thing
Sure,
lifted up by the frost.
Now, one thing we should point out too, in the picture where we were showing a building over the structure, a heated building, with no insulation here, if generally people put insulation underneath slabs.
Yes.
And there's a reason for that. It has nothing to do with frost, it has to do with comfort.
That's right.
We're trying to keep the floor as warm as possible because people are walking on it, whether it's an office or a living space.
Okay.
So this application takes place with the edge
Yeah, let's go
insulation.
back
We
and
go
look at
back
this one, yeah.
to two, is it this one?
Yes,
This one here.
This one here. Now you got to be careful, Tom. If you put insulation underneath here, now you begin to prevent this heat flow.
Right.
Now you've got to exaggerate this over here
Yeah.
because you're going to drive this temperature below 32 again.
Yeah. But you know, it seems to me that when, knowing people who do this, myself included, what we generally see when people build houses in Maine is we see a good gravel base,
Right.
good drainage,
Right.
and the foam insulation underneath. So so many applications you don't see this wing insulation.
That's right.
Because there's good drainage under here.
That's right.
But to me,
Yeah.
if this is a fairly economical foundation, it's prudent to do both.
Yes.
Have a good gravel base, make sure you have excellent drainage, and get the insulation just so Murphy's Law, which is really what we're talking about here, and when we boil it down, is to understand the physics and make sure that we don't have this problem. Usually, excuse me, you're not talking about an incredible investment in insulation to assure yourself that you won't have this as a problem.
And of course, there's another aspect to it. The kind of work that you and I do mainly is to try to help people design heating systems.
Sure.
And we measure R values, and we look at degree days and so on. And if we miss one day in, say, 10 years, the person calls up and says, I'm cold. We put on a sweater and forget it. Because we don't necessarily want to design the heating system for the very worst day in 10 years.
Sure.
But the engineers that write these papers from which I've taken this data, they don't want it to ever fail.
Right.
You want the years when there's no snow cover, when the wind's blowing and the temperature goes to 40 below and stays there. They don't want the slab to heave. So all of these, all of the information that we have in this paper about thicknesses and distances and so on are very safe designs. Because you can't tolerate that once in 100-year failure, depending of course on the structure.
Sure.
If you're just putting something underneath the front steps, so it fails, you can little carpentry, you can get it fixed. But if you're putting a major addition on a house, and if it does lift once in 50 years, and you pull it away from the building, this can be a real serious
I got a
problem.
great example, Alfonderina. That's one we've used on the radio.
Right.
You can't have Alfonderina move, and here you have ice on the inside, so you have all kinds of real serious thermodynamic problems going on. So, well, why don't we go look around? We've got plenty of examples. Now, these aren't all yours either. No. You haven't perpetrated all these mistakes.
No, right.
But we have some great ones to look at. So let's go take a peek.
Okay.
Well, Dick, this looks like it had a problem.
One would think that a professor of mechanical engineering could design a laundry yard.
Well, I'm pleased that you did it. We wouldn't have a prop.
Well, of course, what I did was I wanted a laundry yard that would be stable laterally.
Sure.
So I just took a pipe and put it into a big sonotube and put it right on top of the ground. I said, who cares if it moves up and down? All right? Well, so I put a pipe on here, and then I put the same kind of a laundry yard as I've got here. Well, it worked fine. The frost lifted it up, but that's south that way. And of course, the frost came out of the ground over here first. So the thing just tipped over because it melted on that side while it was still frozen on this side. So now I have changed the design. And I have a piece of channel iron, which I drive in the ground, and I bolt the laundry yard post to that. Then every spring I just come around with a mallet and I drive this back down in the ground, so my laundry yard...
a rite of spring. In other words, come out here with a sledgehammer and beat on the... And now you could have done this also with a piece of pressure treated and not beat it in the ground, but I can see where this would be kind of fun and therapeutic. Winter's over, you come out and beat on the steel.
And of course, the height of the laundry yard is crucial. You see, you've got to be up so you don't drag sheets and things on the ground.
You can get a lot of clothes out here. You've got 1, 2, 3, 4, 5, 6, 7 lines. Boy.
Well, the reason for that is I have a watt-hour meter on the dryer, and I growl at the tenants.
I see. So this is you don't have to pay any gas or electric bill to use this facility.
That's right.
So that's good. All right, let's go across the street. There's another one to look at. Well, gee, Dick, there seems to be a little problem with this foundation. I'm not quite sure what to say. This is the Patch House in Orono. It's a historic structure. Unfortunately, the historic foundation isn't doing very well, and for several reasons. It's sort of a rock and mortar foundation. It looks like they might have even poured over concrete after the fact, trying to reinforce it, but the frost has wrought havoc, and this is one of the issues with this historic property, is the foundation really has gotten shot, and it's compromising the structure of the wood framing up above it.
It's particularly difficult because the building has been unheated. That is, if you got enough of a heat loss out, that violates one of the 3 criteria. That is temperature and frost susceptibility and moisture. And this had it all.
And this is what happens. It just blew it apart. There's no rebar in here. So that just exacerbated it. And of course, once it opens like this, we're really into mischief now because cold air is leaking in. So when the air out here is 20 below zero, the air in there is, I'm expecting somebody to come out and nip my finger. The air in there is 20 below zero, and it just makes it worse. And it's just been a compounding problem over the years to the point where the building is presently uninhabitable, and the whole foundation will have to be restored as part of a historic restoration. Which is sad, but it's not beyond hope. It's just going to cost lots of money.
Yes.
So we have another one out front, same property. Let's go look at that one.
You know, this at one time was one continuous sidewalk and a set of steps. Remember that picture we had in the first slide of those ice lenses forming?
Sure.
Well, every year what happens is, this is a frost susceptible soil.
Yep.
Those ice lenses form and they wedge the steps out. Then of course when it thaws, dirt falls in where the ice lenses
so
were,
we're dropping
and then you
down.
start again.
Yeah.
So these steps someday will be right out in the road, as every year they get wedged a little bit by the frost susceptibility of the soil underneath them.
Well, that's you know, the issue here of these steps too, being masonry steps, should be insulated underneath.
Yes. Yes.
And boy, that's pretty dramatic. You know, you see these things and you kind of become oblivious to them after a while. You think, oh well, but it's striking when you put all this together and understand what's happening with the physics here.
Sure.
The other thing we need to point out, Dick, we haven't mentioned what blacktop does for heat loss.
Yeah.
When you're talking about heat loss, we make wood stoves black because they emit a lot of heat. They radiate heat very effectively. Blacktop does the same thing in terms of radiating heat out of the ground.
Yes.
So where if it was concrete, it would not be as emissive and suck as much heat out of the ground as blacktop does. If this is bare in the wintertime, this will lose more heat than this will.
Right. Particularly if you shovel the snow off of the steps. So the 32-degree freeze line will dig very deep and down underneath the blacktop. That's why it has to be a lot of non-frost susceptible soils and well drained. Okay.
Okay. Here we are on College Avenue, and Dick, I noticed we have to point out your mailboxes, which haven't moved.
That's right.
They're now, and we'll notice there's pressure-treated posts in the background here, and we really are on the road. You can hear the cars going by, because the pressure-treated posts are not moving heat out of the ground. But you said also the
road is up in the air,
and it's well drained.
Well, this is pretty well graveled here,
good
so
soils.
There's good drainage underneath.
Yeah.
So the frost doesn't penetrate, doesn't grab material and give you this edge freeze problem, which lifts posts out of the ground.
And this has been here a long time.
Been a long time.
I remember this for quite some time.
Now, this just sits on by gravity, so if a car hits it, I can just pick it up and put it back on again.
I can always tell when it's a Dick Hill project if it has this slotted channel here. I know it's been. Matter of fact, I might have given you that.
You might have.
Okay.
Yeah, right. Okay.
All right.
This is why they build the sidewalks out of blacktop and not out of concrete. Because underneath here is very obviously a stone.
Big one.
A big one, that's right. And what's happened is that the frost penetrates very slowly out here because of the moisture in the soil and the need to supply the latent heat diffusion of the moisture. Underneath this rock, the rock is a good conductor of heat, absorbs no energy in the process, so the frost goes down very deep on the rock, and ice lenses now form underneath the rock. And that sucks additional moisture from the subgrade. Those ice lenses continue to form and lift that rock right up through the pavement.
I wonder when it's going to be here.
I don't know. We ought to have some.
It's on its way.
It's on its way.
Have a coming out party for the rock. There's another one in back of us.
Yeah, that's right.
So now when you're in a sidewalk, you're walking down College Avenue, you're going to university to classes, you can count the number of rocks that are coming up through. And as an alumni, you come back and someday that rock will be up through the surface and you'll be, you say, I remember back when that was just a hint of something to happen.
I think it's entirely appropriate. You can't tolerate this in the highway.
Right.
So in the highway, much better material, much better drained and all the rest of it. You get to build a sidewalk. Who wants to spend a lot of money on a sidewalk? So you wind up with material that's not well drained with big rocks in it, and you get this kind of phenomenon.
Okay. All right. Well, Dick, thank you for taking the time to explain all this to us. We'll show it at the end of the show, but we have an address where there's a paper you wrote.
That's right.
That has all this information.
Yeah, a PhD candidate in civil engineering, Wei Chen, and I put all this down. We read all of the seminal documents and put it all down. And it's particularized for Maine. That is, you look at any of this stuff, and it's all varies with freezing degree days and all that stuff. Well, you don't have to get into all that because we particularized it for Maine. And the Dean of Engineering has promised that he will send anybody a copy of this that wants to write in. So that's the Dean of Engineering. It's at Barrows Hall at the University of Maine, 04469 5708.
Okay, we'll have that at the end of the show.
Good.
Folks.
Okay. And again, just to drop a postcard to the dean, and he'll put this paper the way Chen and I wrote in the mail, and you'll have all the numbers to look at.
Okay. Well, I thank you for taking the time to explain this to us.
Okay.
It makes a lot more sense now. And I just want to point out we're standing. Dick, aside from being an engineer, is also an artist, and we have here. There was a motif number to this, as I recall.
Yes.
Was it motif number 2? Or?
Yes. Yes.
Okay. Motif number 2 has been reworked in the past couple of years, so here we stand under the new motif number 2.
Okay.
Hey, we'll see you next time.
Production support for Hot and Cold is brought to you by American Solar Technics, manufacturers of components for wood burning and solar heating systems.